Okay, we're going to do this work energy problem with collision. Actually, I'm not going to do it as a work energy problem. I'll do it as ballistic motion. So let's see what we got here. It's a frictionless table, and block A is sliding across and has an elastic collision with block B. So we can use our elastic collision equations. And this table is 85 centimeters above the ground. Okay, and we want to know delta x, how far away from the edge of the table does block B land? Alright, so let's start with the collision. Since it is an elastic collision, now I'm only worried about block B after the collision. Block A is probably going to bounce back off or something like that, but I'm only worried about block B, so we'll call block B block 2. Right? If we look back at our velocity equations on the formula sheet, we have that for elastic collisions, we've got this formula. I guess this is alright. Now we're told that V1I here, or VAI, the initial velocity of block A, is 4.0 meters per second, and V2I, or the initial velocity of block B, is 0. It's at rest. Okay, so so the velocity of block B after the collision is 2 times the mass of block A, which is 2 times 3m over 3m plus m times 4, plus this term times 0. So I really don't care what that term is. Now notice what I've done here. I'm told that that block A is 3 times more massive than block B. So what I've done is I've called MA 3m and MB m. If you want, you could say that MA is 3 kilograms and MB is 1 kilogram. You can actually plug in numbers here if you want, whatever. Either way, it's going to work out to be the same. I could make block A 15 kilograms and block B 5 kilograms. It'll still work out the same way. So this works out to be, let's see, 6m over 4m times 4. And the m cancels out. So 6.0 meters per second. That's the velocity of block B. That's equal to the initial velocity for part 2. Okay, that's the velocity of block B after the collision. Now we need to find out how far away from the table B lands. Sometimes people mistake here block B's motion and they try to do some kind of work energy thing. But actually the easiest way to do this kind of problem is using the methods, the ballistic motion methods that we used back in chapter 9, back in chapter 3. And to do that, you need to make a table. If you haven't already done this, you should. Just for simplicity, my sign convention is going to be that to the right is down, to the right is positive and down is positive, okay? Generally, I like my direction of motion to be positive. Makes things easier. Okay, so in my table, I know that the final velocity from part 1, which is 6.0, is the initial velocity for part 2, and that's horizontal, right? That's 6.0 meters per second. So this thing flies off the table with a horizontal velocity of 6.0 meters per second, which means it has an x component of 6 and a y component of 0. Now the final x velocity is also 6 and the x acceleration is 0. What else do we know? The y displacement is 0.85 and the y acceleration is 9.8. Now you may have made down negative, in which case you would need to make the y acceleration negative and the delta y negative. As long as these two have the same signs, they're consistent, then you'll get the right answer. Okay, so I know 3 out of 5 things in x, but I can't solve x when the acceleration is 0. I can solve the y part. I've got 3 out of 5 things there. I'll use the equation to find, see what I need to do is I need to find time here, plug it in over here on the x. So to find time, I'll use the equation that doesn't have final velocity in it, which is this. So 0.85 is 0 plus 4.9 t squared. That gives me t is 0.416 seconds. And now I'll plug that in over here in the x and get delta x is equal to v naught xt plus 1/2 at squared. Of course, the second term is 0, so I get 6.0 times 0.416, which is 2.5 meters.